Hello everybody. In the last class, we completed with arithmetic instructions. Today we will start with logical instructions. So these are the logical instructions which we will cover today: and, or, exclusive, or, not, and negate. And shift, rotate, and test will probably cover in the next class. Maybe if time permits, I'll cover test also in today's class. Okay. All these operations, okay, all the logical operations are bitwise operations. Okay. Bitwise operations, what do I mean by bitwise operations is like suppose I have a number and I have another number, right? When I do and, okay, of AL and suppose this is BL. So if I do an AND operation, this whole number is not taken as a single number. It is bitwise AND is done. Okay. So 1 0, if you do an AND, it will be obviously will be a 0, 0 1. Okay. So this will be 0, this will be 0, and 1 1 AND operation. So the least significant bit of both these numbers and operation would be carried out. For that matter, any logical operation. So bitwise, the corresponding bits. Okay, so the operation is bitwise. That's why we say all are bitwise operations for this entire set of logical instructions. Right. So the first instruction is and the format is like this: you write and then you specify the destination and the source. Okay. Now why I call this as destination is because the data here finally will be amended and the result will be available here. So suppose I write and ALBL. ALBL, okay, both are 8-bit data. Now if you see this is 0 and this is 0. After the operation, obviously BL, this is the source, so this data doesn't get corrupted. It remains as it is, but the AL register, you have the result of this operation. So 0 and 1 will give 0, right? So from here to here, you see all the numbers are different, and this is 0, this is 1, so obviously this also. So the only place where 1 and 1 is available is in the second bit from the left hand side, and hence I have a 1 here. Okay. So this is another example. Here if you see here, none of the bits are, the corresponding bits are the same. So when you do an AND operation, you get complete 0 here. Here it's all are 1s, so you do an AND operation, you get complete 1. Here also if you see here, none of the bits are, see it is 1 out here, it is 0 here, it is 0 here, it's 1 here. So finally you get an 0 out here. So so this is how after the execution the data of the AL looks like. Okay, for these particular combinations of AL and BL. Right. Now what are the flags which get affected? Okay, so if you see here, these are the 3 flags. Okay, parity, sign, and 0. Okay, they get affected. So all decisions made in the program should be based on these flags. Okay, auxiliary flag is undefined, and CF and OF are programmed to become 0. Okay, so you not take any decision based on this law, right? So programming, while doing the programming, we have to look at only these 3 flags. Now here in this case, it's not a 0, and hence a 0 flag will not be set. In these 2 conditions, it's 0. The result is 0. Okay, and hence they get flagged. In this case also, this result is not 0, and hence it is 0. This is the sign flag. So in the sign flag, it just gets it is set to 1 only if the most significant bit is 1. In this case, this is 1 here, and hence I have the sign. And this is the parity. Now if you see here, this is an odd number of 1s is there, and hence it is 0. Here it is an even number of 1s, that is 0 1s, hence it is 1. Here also even, right? So this is the parity flag. So these are the depending on these parity flag, these 3 flags, and you can further write your program and decide about the branching. Okay, so that's about. And you could also write in this, like all the addressing modes which we studied earlier, same thing is applicable even for the logical instructions. Now if I write and DX and SI, obviously DX is a 16-bit data, right? And hence a 16-bit data will be brought from the memory whose starting address is given by this, right? So this is the offset. So obviously DS plus that physical address would be computed, and from two 8-bit memory locations, consecutive locations, this data will be brought here. A 16-bit data will be there, and then a bitwise AND operation would be carried out. Okay, again these are the same flags. These are the flags which will get affected. Okay, so this only shows that you could do an 16-bit AND operation also. And finally, the answer will be stored in the DX. The 16-bit answer will be stored in the DX. Right. Now, what are the users? Some there could be many users, but these are some of the users. Okay. Now, when I do an AND operation, suppose this is the my original data. I want to force zeros in the first two bits, okay, least significant bits. Okay, so what do? I can do an AND operation with B. Now, if I do this, okay, wherever when I do an AND operation, right, if it is 1 here, the same data gets replicated to the bottom, right? So, whereas if it is a 0 here, irrespective of what is data here, it comes 0 here. So I have masked these two, that is, I have forced 0 into these two bits. Okay, so this is another example. Now if you see here, these are the this is the higher nibble, this is the lower nibble, so this is some unknown number. So when I am doing an AND of this plus this, if I do an AND operation, then here I have the numbers, whereas here zeros will be forced. Okay, similarly there could be a case where I want to force a 0 into the sign bit, okay, and the most significant bit. So I can do AL into 7F hexadecimal. So 7F looks like this in binary, right? So this is one. So for the AL register, right, you have right from A0 to A7. Right, so all these A0 to A6, these bits don't get affected because you are doing AND with 1. So whatever is the content of AL, that doesn't get corrupted. Whereas since you are doing an AND operation with 0, in the A7 bit, a 0 will be forced. Okay, so you are clearing the sign bit, that you are forcing a 0 into the most significant bit. So this can be done. Another useful application of AND is like we all know ASCII code, right? So like for example, all the keys which we have on our keyboards. Okay, so there are many keys. So obviously to represent all of them, an 8-bit is used, and for if you see the numerical values 0 to 9, okay, it is prefixed by 0, 1, 1. So similarly for alphabets, it is prefixed by something else, right? And for the sign, so all the numericals right from 0 to 9, all the numbers in the ASCII code, it is this is prefixed by 3, and then this number follows. Now if I have to convert this input which is coming from the keyboard, if I have to convert it into pure binary, I need to just remove these 3. So all that I need to do is do an AND of that data which is being received here with 0F. Okay, now what is an 0F? It will be 0, 0, 0, 0, and then 1, 1, 1, 1. Right. So these bits, when I do an and these bits will, because it is 1, 1, 1, 1, okay, F, so they will come as it is, whereas these 3, since you are doing AND with 0, that gets set to 0. Okay, so this is how you can do a conversion from ASCII code to 8-bit binary code. You can do that. Okay. This another example out here of utility of an AND instruction, where suppose I have a number, I need to find whether it is an even number or an odd number. So I can do an AND AL1. Okay, what is 1 will be 0, 0, 0, 0, 0, 1. Okay, so all the bits will be 0. And finally, what will be there in the AL? Whatever is the least significant bit. If it were 0, it will come as 0. If it were 1, it would come as 1. Okay. Now, if it were 0, then 0 flag will be set. Right, that means it's an even number. So jump if 0, so jump at 0 means that an even number has been detected. And if in the AL, in the original thing, in the last significant bit is 1, so when you do an AND operation with this number, the least significant bit will come as 1, because 1 and 1 will be 1, right? So in that case it is an odd number, so it will not execute. Since it is not 0, it will not execute this, and it will come down to your odd number and whatever program you require. So this jump instruction can be used subsequently after doing this AND operation. So these are some of the usage of AND instruction. So similarly, I can have an OR. So it's exactly similar to that of AND operation. Only thing is a bitwise OR operation. So 0 0 will give 0, and here it was 1 and it is 1, so it gives 1 here. This is 0 and the third one is 0, so 0 here, and in the fourth case it is 0 and 1. So in the AND we got a 0, but whereas here it is an OR operation, so I am getting an 1. So this is just doing an OR operation. So accordingly, if you see here, here everything is 0, the 0 flag is set out here, right? In all the other cases it's not 0. Similarly, parity, if you see here, they are all zeros, so it is even parity. It is set here. Here I have 1, 2, 3, 4, 5, 6. So even parity. So this is set here. This is odd parity, one single one. 1, 2, 3, 3. So it is odd parity. So this is set to 0. And sign bit also you could see here. So these are the two. Most significant bits is 1. So this is sign is set to 1. So this is only difference from the AND thing is in bitwise OR operation is being done here. So this is how OR. So there are some usages, like we use the AND operation to force zeros. So if I have to force 1 at specific locations, then I could use the OR operation. Now suppose this is all 0 0 and 1 1. So so what when you do with OR, 1 1 will give 1 and 1 0 will give 1. So so if you see here, irrespective of what is here, I get a 1 1 here. So I am able to force 1 wherever I want, whichever bit I want to force 1, that can be done by the OR operations. Here it is all zeros. So whatever was this data available here, that is coming in as it is. So through the 0 they pass, they become transparent and come here. Whereas wherever there is 1, when you do an OR operations, those bits will be set to 1. Okay, so this is this. So this is another example. If you see here, these are all zeros and these are ones. So if you do an OR operation, so all these will be set as 1. Okay, and these whatever is the number, they get replicated out here, right? Same thing, like we saw, we could force an 0 into the sign bit. Now if I have to set a force a 1 into the sign bit, I can do this. So 8 0 right is 1 0 0 0 and 0 0 0 0. So if when I'm doing it with AL, so all these bits in AL will come as it is, but the most significant bit, okay, here in the AL register, since it's an OR operation, the most significant bit or the sign bit will be set as 1. Okay, so that's the usage of OR. Similarly, we can do an reverse, like we learned how to use the AND operation to take it from ASCII to 8-bit. Now from 8-bit, if I have an 8-bit information and then I need to send it to a display, like an display, say for monitor, right? On the monitor, if you see not only the numbers but alphabets also can be displayed. So you need to send this kind of code to the monitor. So this is the result which we got, a numerical answer, and now if you have to convert it into ASCII, we can do an OR operation. So what is 3? It is 0 0 1 0. No, 0 0 1 1, right? 0 0 1 1, and this is 0 0 0 0. So if I do an OR operation with this table out here, so these numbers, right, since it is all zeros, so they will come as it is. Whereas here it is all zeros here, but you are doing an operation or operation with 0011. So this 3 gets inserted here. So this number gets converted into the 8-bit number gets converted into ASCII code. Okay, so this is another option. Right. Similarly, I can have XOR. Now, so obviously, XOR operation we know from our digital design class that 0 0 will give 0, and 1 1 will give 0, 0 1 and 1 0 will give 1. So if you can see, this is 0, this is 0, so I'm getting a 0 here. This is 1 and 1, again I'm getting a 0 here. And it is a 0 and a 0 here, so I'm getting a 0 here. This is 0 and this is 1 and 0 1, I am getting a 1 out here, right? So this is a bitwise, again like a bitwise XOR operation. The flags are also corresponding to that operation. So here 0 flag, this is the only place where I am getting all zeros, so this is set to 1. A sign bit, I have 1 1 here, so these are the sign bits, and here it is even parity. Rest of the first and the topmost, the number of ones 1 2 3 4 5, so this is 0. Here it is 1 2 3, so it is 0. So odd parity, and these are even parities. So this is XOR. Now if I talk about the XOR instruction usage, okay, so if I have a number, if I do an XOR with 0, if I have some bit, okay, XOR with 0, I'll get the same bit, right? So if I do an XOR with 1, so this will get inverted, right? Because if you see 0 0 will give 0, 1 0 will give 1. So whatever is B is coming here, but if I do an B XOR 1, so 1 1 will give 0, 0 1 will give 1. So it is getting actually B complement I get here. So that's what can be done. So if you see here, this is an 0 0 0 0, right? If you are doing, wherever there is a 0, that data will come as it is, and wherever there is 1, this gets complemented. Okay, so if such operations needs to be done, you can do that. Now another application of this is parity conversion. Suppose it is a number, it's an starting with 0, so I want to just say this is an even parity. Okay, so 1 1, right? So it is 1 1. I want to convert it into odd parity by just changing. Suppose this is the most significant bit is the parity bit. Okay, a parity bit can be here also. Generally here the parity bit is placed here as the most significant bit. Now if I want to just change the parity, okay, so I can do an XOR with this, right? So if you see here, these are all zeros, so these numbers will come as it is in the answer, right? Only the parity bit or the most significant bit will get inverted. Now this will become an odd parity bit. So you can do that whenever you have to change from odd parity to even parity, right? So this is the parity bit which we do the coding. So suppose I have to change from even parity to odd parity and also I can do this. Okay, so that is the thing. And another use of XOR instruction is data encryption. So this is the original data. So if this is the this is an encryption key. So when you do an XOR with this, so you will see this data get total mingled up, right? It gets encrypted. Now I send this encrypted data, okay, from the sender. I receive it in the transmitter, and in the transmitter again I do an XOR operation with the same key. I will get back the original result. Okay, once one more XOR with the same number, with this number if I do again XOR of 0 0 1 0 0 1 1 0, if I do one more XOR I'll get back the original answer, right? Now one who is transmitting and one who is receiving should know this key, right? Because this is a jumbled up data, right? And to get back the original data, the encryption key should be known by the receiver, so that he uses that as a decryption key. So these kind of operations are used to for data encryption, right? Another usage is initialization of registers, right? So we can do move AX0, so this AX0 will be set to 0, but in this case since it's a move operation, the flags will not be affected. Okay. Suppose you want the flags also to be get affected. Okay, in that case, what we can do is XOR AX. Okay, in this case, AX again, because it is an XOR operation, 0 0 will give 0, and 1 1 will also give me 0. So the final answer in AX will be 0. But in this case, all the flags also will be set accordingly. So we can use this instruction in case we need to have the flags also affected. Okay. Then I have an instruction which is not bitwise. It's only one bit is shown here. 0 will become 1, 1 will become 0. Okay. Now, if this is the if in AL, so obviously there is no source out here. Okay, not AL means all the bits of this AL will be inverted here. Okay, again. These are the flags which get affected. Okay, parity, sign fit, and sign flag, and the 0 flag. Right. So if I want a ones complement, I can use, okay, not AL. So ones complement will be there in AL. Right. If I have to do the twos complement, then I have to add 1. So after doing a not 1, if I do increment AL, then I will get the twos complement. Okay. But generally, if you want to do the twos complement, then you don't have to do these two instructions. Okay. These two instructions, combined instructions known as a negate is available. Okay. So when I write an negate AL, so in the AL now the twos complement of AL will be available. So you can use this in a single instruction. Right. So this is the last instruction for today, and then in the next class we will talk about the rest of the logical instructions. So this is known as test. Okay. Now test is nothing but a bitwise AND. Logical AND only. Now, what is it different from the AND operation is both the contents of, suppose I write in a test AL and I give some number, right? Then the after doing bitwise AND operation, the contents of AL is not destroyed. Okay, so there is no although we call it as destination and source. So the contents are not in the destination as well as the source are not destroyed. Okay, it continues to hold the previous data itself. Okay, so there is no result stored in either of these registers. Okay, so that is the only difference. It does an AND operation, bitwise AND operation, but the contents of both these are not. So probably it will be better to write here, I guess, source only, right? Okay. So if you see, one of the usages is suppose I have to find whether it is an odd or even. So if I go back to this previous example where we did this, where was it? There was one example which we did whether it is an odd or even. Here, right, odd or even, where we did an AND operation, right? So in this the contents of the AL register was being modified. So if you don't want to that, you just have to check whether it is an OR. So you can do a test AL yeah, with 1, right? 1 is this. So and then you can take the same, whether jump to 0 if it is even number. So the flags will get affected. Okay, but the number of AL, whatever was the contents of the AL, that doesn't get destroyed. Okay, it remains as it is. So so that is one use of test. Okay, so you can use this test just to test whether the result of the previous operation it is come out to be an odd or even. So you can do this, okay, to check whether it's an even number or an odd number in any register without destroying the contents of that register. Okay, so that's all for today. In the next class we will have these some instructions like shift and rotate we have not covered today. So we'll cover these two instructions in the next class. Okay, thanks a lot.